Swayam Prabha. Digital India. Educated India.
We continue our discussion of last lecture. See, notice how the curve goes, this brown curve, and you should notice also that you see this is ending, this brown curve is ending at the at this point, which is K A is equal to zeta. Where was my equation? Yeah, K A is equal to zeta, and beyond that, if this is this part is imaginary. Now, what will happen if I increase the value of zeta? How can I increase the value of zeta? That is very easy to see. You see, you have V0, which is the depth of your potential well. You also have A, which is related to the width. 2A is actually the width of this potential well. So, if you increase the depth of the potential well, you are increasing zeta, or if you increase the width of the potential well, again you are increasing the value of zeta. So, by varying either the depth or the width, you can vary the value of zeta. In fact, if you increase the depth, zeta will increase. If you increase the width, again zeta will increase. So, if you increase the value of zeta, what will happen? Actually, this curve, this point will shift. So, you may have a situation where the curve would look like that. Correct? And then how many solutions do you get? The answer is there are now 3 solutions. That means actually by increasing the depth or the width, the number of states, number of bound states that exist in your potential well will increase, okay, which is of course physical, right. By increasing the width or by increasing the depth, you will cause more bound states for the system. Now, suppose I did the other thing, I decrease the depth or the width, what will happen? This point is going to shift, okay. So, for example, if I decreased it to that value, zeta is having this value, then what will happen is that you will have such an appearance for the curve, because you see at k equal to 0, the function is always infinity. So, the curve will go like that to infinity. So, now you have only one bound state, correct, but can I get rid of that one bound state? I do not want any bound state. Is that possible? Well, whatever you do, see the value of zeta will be very small, it may be here, still the curve would go like that, and therefore, you will find that there is actually one solution. So, however weak the potential is, right, it does not matter whether it is very shallow or whether it is very narrow, it does not really matter. You will always have one bound state. This is something that happens in one dimension. Actually, if I were thinking of bound states in 2 dimensions, this does not happen. This is a speciality of one dimensional systems. If you have a potential, it does not matter how weak it is. If you have an attractive potential well, then it will have at least one bound state. Okay. Now, here I have analyzed the even solutions. How would they look like? I mean, if I was going to plot them, let me make a picture showing the plots. this is my potential well, let me say, and I have found the values of k, these special values of k I have found, and those special values of k can be put in here, and then I can solve for epsilon. Epsilon will give me the allowed energy levels. So, that is the procedure. If you, I mean, you can use a computer program, specifically if you like mathematics, and get the values of epsilon, and then once you know the values of epsilon, you can put those, or if you know the values of k, you can put those in here, and then of course you will have to determine these constants B1 and C1. How will you determine them? Well, continuity of wave function has to be there. In addition to that, you have to ensure that the wave function is normalized. So, therefore, all the constants that you require can be found, and how would it look like, the wave function? The lowest possible state, as we know, as I have been repeatedly saying, it would not have any nodes. So, the wave function would look something like that. Now, interestingly, you see, if you look at the wave function in this region, how does it appear? The functional form is C1 e to the power of minus kappa x, that is the functional form in this region. So, in that region, the wave function is non-zero. Notice, it is non-zero, it penetrates into that region, into this region, and therefore, what is going to happen is that the function would decay in some such fashion. It would penetrate into this region. Now, this is against classical mechanics actually, because in classical mechanics, if the particle has that much energy, this line represents the energy of the particle. The potential energy of the particle, if it entered into this region, would be so much. So, this is the region where the total energy of the particle is less than the potential energy, right. See, here the total energy of the particle is shown by this line. Okay. Well, I think I should modify what I said. See, this particle, classically speaking, what it will do is, it will hit this potential wall and will be reflected. So, it does not enter into that region, correct. But quantum mechanically speaking, if you look at the wave function actually exponentially decays into that. So, therefore, there it is possible for the particle to be found in that region also, but with a very small probability. This is essentially because of the wave nature. You see, a wave does not terminate abruptly, it will only be terminated smoothly, and that is the reason why the wave function enters into that region. Similarly, on the other side, again the wave function would decay exponentially. So, this is the first possible state. The next state is this one, but I am not going to draw it. Why? Because I have not found it. Why? Because you see, the next state has to be antisymmetric. The lowest possible state is symmetric, the next one is antisymmetric, and the next one, which will be somewhere here, will be symmetric. And how would it look like? It would look like this. Well, let me very quickly tell you what happens with the odd functions. What will happen is quite simple. Okay, what will happen is quite simple. You won't have this B1 cos kx in this region, but instead odd or antisymmetric. It essentially means that if you replaced x with minus x, the wave function actually changes sign. So, if that was the way the wave functions were, then what will happen is that right in the middle the function would have the form B2 sin kx. The other cos kx term cannot be there because your wave function is antisymmetric. If you replace x with minus x, the function has to change sign. So, then you will have to impose the boundary conditions. What are the boundary conditions at x is equal to a? What you will get is B2 sin Ka must be equal to C1 e to the power of minus kappa A, right. This is what you are going to get, and the derivative, this is actually the continuity of the wave function. The wave function at this point, at this boundary, wave function at the point x is equal to a, which is the boundary between regions 2 and 3, has to be continuous. Then the derivative of the function also has to be continuous. I can easily write it. I will just write it because I would like to finish this part quickly. If you evaluated the derivative at the boundary using the two functions, the function on the right hand side as well as the function on the left hand side, and then put them to be equal, this is what you are going to get. And just as before, what you will do is you will take this divided by that equation, so that your K B2 and C1 will disappear. Answer will be cot Ka into K must be equal to minus kappa. That is the result that you will get, which I can rearrange as minus cot Ka is equal to kappa by K, and you remember the manipulations that we did earlier. Kappa by K can be written as kappa A by Ka, which may be written as zeta square minus Ka square with a square root divided by Ka. So, earlier our transcendental equation was this one. All that has happened is, instead of having tan Ka, the left hand side has been replaced with minus cot Ka, that is all. Other than that, there is no difference. This function has changed. So, let us make a graphical analysis again in a very quick fashion. What is this? Actually, this is just that the right hand side, right. The right hand side is what I have plotted now, and then the other thing that I should plot is minus cot Ka. Well, let me just make a plot of minus cot Ka. It looks like this. It becomes a 0 at pi by 2. and then goes on to plus infinity. At pi. So, that is how it is. So, the way I have drawn these curves, how many bound states of antisymmetric nature? Two of them, because you have two intersections. So, one is here and the other is there. And of course, just as before, if I increase the number of if I increase the width or the depth, the number of bound states will increase. But suppose I decrease, I make the potential weaker and weaker and weaker, what will happen? If you made it weaker, see, I can make it weaker and have it in this form, that is a possibility, but it is also possible for me to make it fairly weak, so that the curve will terminate here, so that there is no intersection. So, if you made the potential weaker, you will find that it is not necessary that there should be a bound state of antisymmetric nature. There will be one bound state, but that will have the which nature? It will not be antisymmetric, but it will be symmetric, right. So, therefore, what happens is that the lowest possible state will always be there. The lowest possible state or the symmetric state will always be there, but it is not necessary that there should be an anti-symmetric state. Okay, and having seen that, let me draw this antisymmetric function in the same picture. How would it look like? Well, it is going to be obviously 0 at this point, and then it will do that. So, that is the way the wave function will be. Okay, now you see, after having seen the bound states, strictly speaking, what I should do is I should consider the situation where the total energy of the particle is greater than 0, right. So, that means I have a particle which is having that much energy, and it is going to move towards this potential, let us say. Now, I shall not analyze this in detail, because I am going to analyze a related problem which essentially is tunneling in detail. Therefore, I will not analyze it, but it is fairly simple. This particular problem is fairly simple. What happens is that, you see, what here I have a particle. What happens is that the particle is coming from infinity, let us say, with some energy. It feels the presence of a potential well, right. But then what will happen? The particle can simply go. It can go. It is also possible, actually, strictly speaking, even a potential well can cause the particle to be reflected. This is peculiar to quantum mechanics. If we have even a potential well, the particle need not go to the other side. This potential well can reflect the particle. We will see similar things happening when we think of a potential barrier. Therefore, I am not going to describe this, but in order to be complete, I should tell you what happens. But a particle that is coming from infinity, the energy is my choice. I can choose whatever energy that I want, and therefore, actually I can choose it to have any energy between 0 and infinity, right. So, therefore, you will find that all energies above 0 are allowed. There is no quantization or anything. You again have the particle can come in with any energy that I choose. So, therefore, I will say okay, the allowed energy levels, if you like, they form a continuum which essentially means that the allowed energy levels can be anything. So, if you made a plot of the allowed energy levels for the system, how would it look like? Well, you have 1, 2, 3 discrete states which are bound, and then starting from 0, when you can say okay, instead of drawing it like this, you can say you have energy levels which are extremely close like that, and therefore I say okay, all energies are possible, and in the continuum there is no quantization, nothing. So, that is how the eigenvalues or the allowed energy levels of this system are. Fine. Thank you for listening.